Starting from just this very simple formula for calculating the probability of an event, we can infer or derive uh, several different axioms and properties that are both interesting and are going to be useful to us as we get further into our conversation about probability. So rather than just telling you what these are, I'm going to look at some examples that illustrate these properties so that we can kind of see where they come from. And along the way, we'll get some more practice using this formula here. So first, I have something called a contingency table. This is the results of a survey. A person went out and they talked to 392 people, and they asked them two questions. What's your age? And what's the highest level of education you've achieved? And this table summarizes the results. Okay, and based on this information, I want to calculate the probability that a randomly selected person was under 25. Well, there isn't a single under 25 category, but that's okay. Under 25 is a combination of the under 21 and 21 to 25. So based on that, I can get my formula out. The number of people under 25, remember that's the size of the event. So that's my numerator. It's 128 plus 120. And the denominator is the total size of our samples, 392. So that gives me a probability of 0.633. Now, I want to look at this in a little more detail. Right? Under 25, we can think of under 25 as being either under 21 or 21 to 25. Right? And that is the same as under 25, right? So that is going to equal that fraction, 128 plus 120 over 392. Now what I'm going to do is I'm going to split that fraction apart. I'm going to make it 128 over 392 plus 120 over 392. And now if you look at these closely and compare them to the numbers in the table, you'll see that 128 over 392 is the probability of randomly selecting someone who is under 21, and 120 over 392 is the probability of randomly selecting someone between 21 and 25. Okay, so I want you to compare the first side of the equation to the end of the equation. Right? The probability of under 21 or 21 to 25 is equal to the sum of the individual probabilities. And that brings us to our first property. We're going to assume that we're working from some sample space and we have a probability function, P, from our sample space to the real numbers. Right? All this probability function is it's a function that takes an event and gives us the probability of the event. The first property here summarizes what we just saw. If A and B are disjoint, that is, if their intersection is empty, they don't overlap if you're thinking in terms of the contingency table, then the probability of the union of A and B is equal to the probability of A plus the probability of B. It's our first axiom. Okay, so let's try another one here. Based on this same table, what's the probability that a randomly selected person was over 30? Okay, well, there were no people over 30 in our survey. Our survey maxes out at 30 years old. But that's okay. We can still use our formula. We can still get an answer. The size of our sample space is, the size of our event space is 0. There's nobody in it. Size of the sample space is still 392. So that gives us a probability of 0. Okay, now let's generalize this. Right? My general rule is going to be that the probability of the empty set, the probability of a set with no events in it, is going to be 0. So let's try another one here. Very similar. What's the probability that a randomly selected person was under 30? And now I'm going the other way. Right? Well, use the formula. The number of people under 30 in the survey is 392. That's our numerator. The denominator is still the sample size. That's 392. 392 divided by 392 is 1. All right, so again, let's summarize. Let's generalize this. Right? People under 30, that represents the entire sample space. So what we're seeing here is that the probability of the sample space itself is going to equal 1. Okay, so I've summarized our properties here. The first one is the one we saw before about the union. The probability of the empty set is 0. In other words, the probability of an event that can't happen is 0. The probability of the sample space is equal to 1, or again, kind of thinking the same way, the probability of an event that always happens is 1. And those two results are, in fact, bounds on our probabilities. Probabilities have to be between 0 and 1 inclusive. So I've got another one here. And at first glance, this looks very similar to what we did when we were driving that first property. We want to know the probability of randomly selecting someone who is under 21 or who has high school as their highest level of education. Well, we saw with the previous or probability, when it was the union of two groups, we just added the individual probabilities. So this would be the probability that someone is under 21, that's 128 over 392, plus the probability that their highest level of education was high school, that's 271 over 392. Well, hopefully you see, just from the addition here, that this can't possibly be the right answer. We ended up with 399 over 392, and that's greater than 1. And our probabilities can't be greater than 1. Okay, so what happened? What happened was that the requirements to use that property weren't satisfied. If we look at the under 21 category, that's this group. And if we look at the high school category, that's this group. And you notice that there's overlap. These groups are not independent, right? So the problem are those 120 under 21 and high school students. They got counted twice, right? They got counted once in each group. So we can fix this just by subtracting them out, right? I've got 128 over 392. That's the probability of under 21. I've got 271 over 392. That's high school. Minus 120 over 392. That's the probability under 21 and high school. That's the intersection, the non-empty intersection of my two events. And that gives us a probability that's much more realistic. 0.712, that's a perfectly reasonable result. Okay, so that brings us to our generalization, right? What we did to find the probability of under 25 or high school was we found under 21 plus high school minus under 21 and high school. Right, and that's our next property of these probability functions. In the case where A and B are not disjoint, then the probability of the union of A and B is the sum of the individual probabilities minus the probability of the intersection of the two events. Okay, let's take a look at what I've got here. This is just our formula from the previous slide. Right? I've got the probability of A or the complement of A. What does that equal? Well, our formula says that this is the probability of A plus the probability of the complement of A minus the probability of the intersection. But I want you to think about that intersection for a minute. Right? The intersection is disjoint. Something can't be in both A and the complement of A. That means that A intersection A complement is the empty set, and we saw with the previous axiom, the probability of the empty set is 0. Okay, so that takes care of the right-hand side there, but how about the left-hand side? A union A complement. That's the entire sample space. And again, applying our previous axioms, the probability of the sample space is 1. So my whole equation there turns into 1 equals the probability of A plus the probability of the complement of A minus 0. And that's our next property. Right? This is it's called the complement rule. The probability of A plus the probability of the complement of A has to equal 1. Or sometimes we'll think of it this way. The probability of A is equal to 1 minus the probability of the complement of A. I just subtracted the complement from both sides. Right? This is a little equation that's going to be really helpful evaluating certain kinds of probabilities. Okay, so I've added that to my list here. So now in addition to our 3 axioms, we have these 2 properties. that we'll use as we go forward to answer a variety of probability questions. Okay, so in the next lecture, we're going to look at some specific probability questions, and we'll see some of the ways that we can apply these properties and axioms to answer those questions.